Hi guys, welcome to this video where we are going to start a new topic, that is augmenting data structures. So what all things we are going to cover in this video? First of all, we will see that what do you mean by augmenting a data structure, and then we will look at the methodology or the steps we need to follow in order to augment a data structure, right? And then we will revisit Augmented Stack and we will apply this methodology or the steps that we learn in case of Augmented Stack. And mainly we are going to focus on this example of augmenting red-black trees, where we will learn how do we add different operations like select and rank in case of red-black trees, right? So this is going to be a very interesting video. So first of all, what do you mean by augmenting a data structure? So suppose you have a data structure. Suppose you have got a red-black tree, and if you have watched my videos of red-black trees, you will know that in case of a red-black tree, we can perform three operations that are search operation, insert operation and delete operation, right? And we can perform all these three operations in big O of log n time, right? For searching a node, it takes order of log n time, and for inserting and deleting a node, also it takes order of log n time, right? Because red-black trees are balanced binary search trees. So I have made many videos of red-black trees in this advanced data structures playlist. I'll provide the link to those videos in the side button. You can go and watch it there. So let us come back to augmenting a data structure. So here we have got a data structure that is red-black trees, and in red-black trees we can perform these three operations, right? Normally we perform these three operations. But suppose if I want to include another operation in case of a red-black tree, like I want to also find out this ith smallest element, like I want to find out, for example, the third smallest element, the fifth smallest element. If I want to find out the ith smallest node, so to perform such an operation in red-black trees in an efficient manner, I need to modify red-black trees, or I need to modify the nodes in the red-black tree, right? So if I want to perform this operation in red-black tree, I need to modify my red-black tree, or I need to add some extra information in each and every node of a red-black tree so that I can perform this operation, and I can perform this operation efficiently. I don't just have to perform this operation, but I also have to perform this new operation efficiently in case of a red-black tree. But at the same time, I want that when I modify my red-black tree, in order to perform this new operation efficiently, the efficiency of these already existing operations should not reduce, or the time complexity of these already existing operations, it should not go down. I don't want that to happen. So I have got two aims. The first aim is that I need to perform this new operation, find out the ith smallest node in an efficient manner. And my second aim is that I don't want that while I perform this new operation on my red-black tree, these already existing operations efficiency goes down. I don't want that to happen. So these are the two aims. So in order to achieve these two objectives, I need to modify my data structure, or I need to modify my red-black tree. And this modification of the data structure is known as augmenting data structures, right? So basically, augmenting data structures is the modification of the data structure in order to achieve two objectives. The first objective is that you need to perform a new operation on the data structure in an efficient manner. And the second objective is that the efficiency of your already existing operations, like in this case search, insert and delete, the efficiency of those operations should not go down, should not decrease, right? And for that you need to modify the data structure, you need to add some extra information in the data structure, and this process is known as augmenting data structures, right? So now you can easily understand the steps or the methodology that we need to follow in order to augment a data structure. So these are the steps. In the first step, we choose a data structure, right? We actually choose a particular data structure which we need to augment. Like in this case, that data structure was red-black tree. So I needed to perform this new operation on this data structure. So first of all, I have to choose that which data structure I have to augment. So in this case, it was red-black tree, right? So first of all, we choose a data structure, and in the second step, we actually determine the additional information that is required in order to perform this new operation efficiently. We don't just have to perform the operation, but we also have to ensure that we perform that new operation in an efficient manner, right? So we need to determine that what additional information do we have to store in this data structure so that we can perform this new operation efficiently, right? And it is not necessary that we just perform one new operation. There can be many such new operations which we want to perform on this data structure. So accordingly, we have to determine the additional information that will be required, or the modification that will be required in case of a data structure, right? And in the third step, we actually develop the new operation, or we write the pseudo code for the new operation. How does this new operation work? For a particular condition, do we have to go to the left child or the right child in case of a red black tree, right? So all these internal working of the operation is actually determined in the third step, right? And in the fourth step, we need to verify that the efficiency of the previously existing operations is not reduced. The efficiency of the already existing operations should not go down when we add this new operation in our data structure, right? So this is something that we need to verify after we have completed the first three steps, right? So I hope you have also understood the steps that we need to follow in order to augment a data structure. Now let us look at a very simple example of augmented stack. So now let us look at a very simple example of augmented stack. You must have learned that in case of a normal stack, we actually perform only two operations, that is push and pop. Okay, these are the two operations that are performed in case of a normal stack. Some of you might also say that we also perform this operation, that finding out the top element of the stack, but for time being, let us ignore this operation. So we just perform these two operations in case of a stack, right? And we know that the time complexity of both push and pop is order of 1, right? We know that both are constant time operations, right? Now suppose I want this stack to perform another operation or another new operation, that is multi-pop of k. Okay, I want my stack to also perform this operation. So where k is the number of elements that have to be popped out at the same time, right? In case of pop operation, we just pop a single element at a time, but in case of multi-pop of k, we can pop out more than one element from the top of the stack, right? So now I want to define this operation multi-pop of k. So if we want to define this multi-pop of k, it will look something like this, that it will return a boolean value and it will return false when k is greater than n. Of course, when the number of elements that you want to pop out of the stack are greater than the number of elements present in the stack, that is not possible, right? Here n is the number of elements in the stack. So that is why it returns false, because the number of elements to be popped out should always be less than or equal to the number of elements in the stack, right? The number of elements that we have to pop out at the same time, right? So so otherwise it returns true, right? So this was the multi-pop of k operation. So here we actually did the third step, where we developed the new operation, or we learned that how this operation will work, right? It is very simple. Then I forgot to mention the first and second step. So in the first step, we chose a data structure. Here we chose a stack. And what does the second step say? Determine the additional information required so that you can perform this new operation efficiently. In the case of multi-pop of k, we do not require to store any new information. So what do you think can be the worst case time complexity of this operation multi-pop of k? So in the worst case, k can be equal to n, right? When k is equal to n, that can be the worst case, because you want to pop out all the elements in the stack, right? So each pop will take order of 1 time into the number of elements you want to pop out, that is equal to n. So that will be order of n. So the worst case asymptotic time complexity of multi-pop of k will be order of n. But I have already taught in the amortized analysis video of this advanced data structure playlist that for multi-pop of k, the amortized time complexity is order of 1. It is not order of n, right? And when we perform multipop of k, there is no change in the time complexity of these two operations, right? Even if you think, you will understand that when we add a new operation like multipop of k, there will be no change in these operations, push and pop. They will work as they were working earlier, right? In order of one time, right? So of course, we also verified that the efficiency of the previously existing operations is not reduced, right? As you can see in this case. So this was a very simple example of augmented stack. Now let us look at a more complex example in which the data structure that we will choose is red-black trees, okay? So now let us look at the example of augmenting red-black trees, okay? So this is a red-black tree. As you can see, each and every node is either red or black, and the root is black, and there are no consecutive red nodes. So I've explained each and everything about red-black trees through many videos in this Advanced Data Structures playlist. I'll provide the link to that video in the side button. You can go and watch it there. But let us see, how do we augment red-black trees? So as I already mentioned, in red-black trees, you can perform three operations. That is search, insert, and delete, right? Now suppose you want to perform these operations in the case of a red-black tree, but in addition to that, you also want to perform two new operations. Like suppose you want to find out the rank of any node in this red-black tree. What do I mean by rank? That if I do an in-order traversal of this red-black tree, then what will be the position of that node? Like in this case, the rank of D will be 1, because in case of in-order traversal, D will be the first node, right? So if I want to find out the rank of any node in the tree, that can be one operation. So we will see two such operations. We will see how we can perform them in case of red-black trees while not disturbing the time complexity of these operations and also performing those operations in an efficient manner. So we will look at all these steps when we perform those two new operations in case of a red-black tree, right? Or in short, we will augment red-black trees. This is a normal red-black tree. We will see how do we augment a red-black tree. So suppose apart from these three operations, we want to perform these new operations in our red-black tree, right? The select operation and the rank operation. So what is the select operation? So this select operation, it returns a pointer to the node containing the ith smallest element of the subtree rooted at x, right? Suppose if we choose a node x as the root of a subtree, so the ith smallest element in that subtree will be our target node, right? So in this case, a pointer is returned to the ith smallest node in the subtree rooted at x, right? Whereas in this operation rank, it returns position of the node x if we do an in-order traversal of the entire red-black tree. What will be the position of this node, of this particular node, when we do an in-order traversal of the entire tree? For example, what will be the position of node I when we do an in-order traversal of this entire red-black tree? Whereas in case of select function, we will first choose a node as x and we will find out the ith smallest element in this subtree that is rooted at x or rooted at f in this case, right? So that is the select function. And in case of rank operation, we again choose a node x and we return the position of this node when we do an in-order traversal of this entire tree, not the subtree but the entire red-black tree, right? So in this case, what will be returned? When we do the in-order traversal, as the position of f is 2 in in-order traversal, first we come to D, then F in in-order traversal. So as the position is 2, so 2 will be returned when we perform the rank operation, right? So I gave you a brief idea of these two operations. We will also write the pseudocode for both the operations, right? But now let us go step by step. So in the first step, we saw that we need to choose a data structure, right? So we have already chosen red-black trees as a data structure that we need to augment, or that data structure where we need to add new operations, right? So the first step is done. And in the second step, we want to determine the additional information that will be required in order to perform these operations in an efficient manner. Look, even if we don't add any information in the red black trees, we can still perform this operation. For example, if I want to find out the rank of any node x, if suppose I consider this node x, right? If I want to find out the rank, I can find out by doing an in-order traversal, and I can find out the position of that node in in-order traversal. But what will be the time complexity of that operation? It will be order of n, because in the worst case, if you ask me to find out the rank of this node, I'll have to traverse each and every node in the in-order traversal. So the worst case time complexity will be order of n. But all these operations you see over here that were already performed in a red black tree are performed in order of log n time, right? And we want to perform even this operation in an efficient manner, or perhaps in order of log n time. So because of that, we actually need to modify this red black trees. We can't just simply perform this operation without doing any modification in our red black tree, right? So that is why to perform both these operations efficiently, we will modify our red black tree, or we will augment the red black tree. So now let us determine the additional information that we need to add in our red black tree so that we can perform these operations efficiently. So how does the node of a red black tree looks like? So usually the node of a red black tree has a data value, right? So this will be a character in this case, but usually it is numbers like 8, 10, 6. But here I have written characters as nodes. So this will be a char value. And then there is going to be a pointer to the left child and a pointer to the right child, right? Moreover, in case of a red black tree, the color of the node is also stored for each and every node, right? So that will be a bit value. So usually this is how a node of a red black tree looks like, right? But in order to perform these two operations as well, I have to store some additional information in each and every node of the red black tree. And that additional information will be size of x, okay? That will be size of any node x. So what is size of x? So size of x is actually the total number of nodes in the subtree rooted at x. For example, if I take this node f as x, okay, so what will be size of f? Size of f will be the total number of nodes in the subtree. This is the subtree that is rooted at x, right? So what will be size of x? 1, 2, 3, 4, 5. There are total 5 nodes in the subtree rooted at x. So size of f will be 5, right? So size of x is the total number of nodes in the subtree rooted at x, right? And we also include the node x when we calculate the size of x. Like here, I've counted this node as well in the subtree rooted at x. I've added f as one of the nodes in the subtree rooted at x. And we don't calculate the null nodes or these nodes that we saw earlier in red black trees, right? We don't calculate these nodes in the subtree rooted at x when we calculate the size of x, right? So how can size of x be calculated? Or how can we calculate the number of nodes in the subtree rooted at f? So that will be equal to the number of nodes in the subtree rooted at its left child plus the number of nodes in the subtree rooted at its right child, right? So now that will be equal to the number of nodes in the subtree rooted at d plus the number of nodes in the subtree rooted at I plus 1. Why plus 1? Because we are also including this node f when we are calculating the size of f, right? So how can we write it down? So size of x, so we can write down size of x is equal to size of left of x, or the size of the left subtree plus the size of right of x, the size of the right subtree plus the node itself, right? Plus 1. So that is how we calculate size of x. Now let us calculate the size of x, or the size of each and every node in this red black tree, right? So what will be the size of j? How many nodes are there in the subtree rooted at j? Only one node, j itself, right? So the size of j will be 1. And what will be the size of g? The size of g will again be 1. What will be the size of I? The number of nodes in the subtree rooted at I. 1, 2, 3. So the size of I will be 3. And the size of d will be 1. And the size of f, we calculated it will be 5, right? 1, 2, 3, 4, 5. And the size of T is again 1. Size of S, the number of nodes in the subtree rooted at S, 1 plus 1, 2. Okay. And what will be the size of P? So we can calculate the size of any node using this formula as well. Size of the left subtree plus size of the right subtree plus 1. So size of the left subtree is 5 plus size of the right subtree is 2. 5 plus 2 plus 1, the node itself, right? So it is 5 plus 2 plus 1, 7 plus 1, 8, right? So size of P is 8, right? So we have calculated the size of X for each and every node, right? You will very shortly understand that why this is the only new information that we require to add in each and every node so that we can perform these two operations efficiently. You will understand this very shortly. So now in the second step, we have determined this new information that needs to be added in our data structure red-black trees. In the third step, what do? We develop the new operation. So first of all, let us choose this operation, select, okay. So we will develop this new operation, or we will write the pseudocode of this new operation, or we will see that how this operation can work in case of a red-black tree, right? So let us look at that. Now let us perform this select operation in case of a red-black tree, okay. But in order to perform this select operation, we need to know the rank of each and every node, right? So what is rank of each and every node? It is the position of that node when we do an in-order traversal of the tree, of the entire tree, right? So it is the position of that node. So if we do the in-order traversal of this tree, let us do the in-order traversal, and I am denoting rank as R, okay? I am denoting rank as R. So now if I want to find out the rank for each and every node, so let us do an in-order traversal to find out the rank of each and every node. So in the in-order traversal, D will come first, right? So D, and then we will have F, okay? F will have rank 2, G will have rank 3, and I will have rank 4, J will have rank 5, and the rank of P is 6, the rank of S is 7, and the rank of T is 8, right? So these are the ranks for all these nodes, right? So rather than finding out by doing an in-order traversal, so we are assuming that we have already done that second operation, rank T comma X, before we do the select operation, and now we are trying to add this select X comma I. So now after we have got this information of the rank of each and every node, how we will perform this operation select X comma I. So first let me write down the pseudocode for this operation, and then I'll explain it to you with the help of an example. So this is the pseudocode for this select operation, right? And here I is the parameter I, whereas R is the rank of a node, right? So you will understand the pseudocode when we see an example. So let us consider our P as X when we perform the select operation, right? This is our X, and we want to find out the fifth smallest key in the subtree rooted at the node P, right? Or rooted at X, right? We want to find out the fifth smallest key. So we can write it down as select P comma 5, right? So we are going to use this pseudocode to solve this example. So as you can see, this is a recursive function, and we will use this pseudocode in order to solve this example, okay? So now, what is my I in this case? My I is 5, and what is R? R is the rank of P, right? So what is R or rank of P? We can check over here. The rank of P is 6, right? So rank of P is 6, okay? So in this case, I is less than R, 5 is less than 6. So we go to the left child of P, right? We should go to the left child of P. So what is the left child of P? It is F, right? F is the left child of P. So now we can write the next recursive call as left of P. So left of P is F, right? Comma I, right? I. And I was 5, right? I will remain same. So even if you think, you will understand that when we want to find out the fifth smallest element in any subtree, but that node is actually the sixth smallest element. It is not the fifth smallest element. So obviously that element is greater than our target node. Our target node is the fifth smallest element in this subtree. So obviously when this node is greater than that target node, so we are going to find that target node in the left subtree, right? That is why we are actually doing a recursive call on the left child, right? So in this case, select f comma 5. What is I? I is 5. And what is my r? R is the rank of f. What is the rank of f? It is 2, right? So r is 2, okay? So this node f is actually the second smallest element in our entire subtree or the entire red black tree, but we are looking for the fifth smallest element. That means that target node or the fifth smallest element is greater than f, right? So in such a case, we need to go at the right subtree of f, right? Because we are looking for a node that is greater than f. So in such a case where your I is greater than r, you go to the right child or you do a recursive call on the right child, right? So now from f we will go to I, right? And our next recursive call will be select I comma. So here the parameter we are writing as I minus r. Why? These are the smaller nodes. All these nodes, that is f and its entire left subtree, is actually smaller than where we are going, right? So all these nodes over here are greater than f and the left subtree of f, right? So we need to discard those nodes in our calculation and we need to consider a new subtree, right? So when we were looking for the fifth smallest element, we were actually also considering these nodes. But as now we are going to the right subtree, these nodes are no more into our consideration, right? If you think a little bit on these lines, you will understand that why we are writing I minus r instead of I, right, in this recursive call. So here I minus r is, I is 5 and r is 2. So 5 minus 2, 3, right? So this will be the next recursive call. So now we have got select I comma 3, right? And we were looking earlier for the fifth smallest element, but now we are looking for the third smallest element, right? We are looking for the third smallest element. So now we cannot consider this list as the rank of all the nodes because our x has transferred from year to year in our new recursive call, right? So now we are looking at this subtree rather than this entire subtree or the entire tree, right? So now what will happen is that these ranks, they will be updated for this entire subtree. If I look at the ranks of each and every node for this entire subtree that is rooted at I, so for that I'll do an in-order traversal. So first the rank of G will be 1, the rank of I will be 2, the rank of J will be 3, right? Okay, so now the reason I have updated the ranks is because I'm no more considering this entire subtree. My subtree has changed and I have taken this subtree that is rooted at I as the new subtree, and in this case the ranks of each and every node will change. So there are only 3 nodes in this subtree, so the ranks of these nodes have changed, right? So now I'll look at these ranks, right? So in this case my I is 3, right? It is no more 5. I'm looking for the third smallest element in this subtree rooted at I. And what is the rank of I? What is the rank of this capital I or the node I? The rank of I is not 4, it is 2. Why? Because I have updated the ranks when I move to the right subtree, because I'm no more considering all these nodes, right? So the rank of I is 2, so R is 2, right? So this is a case where I is greater than R. That means we are looking for the third smallest key, but I is actually the second smallest key. So that means we are looking for a node that is greater than this node I, right? We are looking for a node that is greater than the node I. So we need to move to the right subtree, right? So even intuitively you will understand that we need to move to the right subtree. And apart from that, we will no more consider these 2 nodes, I and its left subtree. Why? Because we are moving to the right subtree. Now this will be our new subtree. the subtree that is rooted at j, right? So if I write the next recursive call, it will be, so what is the right child of I? It is j, right? And what is I minus r? I is 3, r is 2. So 3 minus 2 is 1, right? 3 minus 2 is 1. So now I've got this new subtree that is rooted at j, right? So in this case, now even my ranks will get updated. The rank of j will no more be 3. Why? Because I've got only one node in my subtree. How the rank of that node can be 3, right? How the position of a node in a subtree with only one node can be 3, right? So I'll also update the ranks, and the rank of this single node in my subtree will be 1. So the single node is j, so its rank is 1, right? So here the rank of j is 1, right? And my I is also 1. So in such a case where r is equal to I, or when I is equal to r, we return this node, or this is our target node that we were looking for when we did our first recursive call, right? Or in other words, this j is the fifth smallest key in the subtree that is rooted at p, right? So we will return j because it is the fifth smallest key in the subtree rooted at p. We can also cross check. So if we want to find out the fifth smallest key in the subtree that is rooted at p, so we can also cross check that when we do an in-order traversal, all the elements will be sorted, right? So which is the fifth element? That will be the fifth smallest key. So if we do the in-order traversal, first d, so this will be the first element, this will be the second element, third element, fourth element, and fifth element. So the fifth element is j. Yes, our calculation is right. And this is how we perform the select operation that I have explained through an example using this pseudocode, right? So for practice, you can also find out select f comma 3, okay? So you can also solve this yourself and let me know in the comments that what is the answer for select f comma 3, or which node will be returned when we do this operation select f comma 3 for this red black tree. So this was our augmented red black tree when we added this new operation, that is select x comma I. So what was the time complexity of this select operation? As you can see, in each and every step, we are actually traversing along the path, right? We are going downwards. So the time complexity will be of the order of the height of the tree. And the height of the red black tree, as it is a balanced tree, is always of the order of log n. So the time complexity of the select operation will be of the order of log n. So the time complexity will be order of log n, right? So now let us look at the next operation, that is the rank operation. So now let us look at the second operation that we need to add in our augmented red black tree, that is the rank operation. So what does the rank function return? It returns the position of node x when we do an in-order traversal of the entire tree. Like suppose when I say rank t comma s, that means I'm asking for the position of node s when I do an in-order traversal of the entire tree. So basically that is what I'm asking for. So now rank of s can be found out if we do the in-order traversal. But when we do the in-order traversal, it will take order of n time, right? It will have a higher time complexity. So can we reduce that time complexity in order to find out the rank of any node? Let us see. So for that we can use this code, right? So I'll explain this code with the help of examples. So when I say t, I mean the entire tree, and x is my target node whose position I want to find out when I do an in-order traversal of the entire tree, right? So for example, if we take our x as f, okay, this is our x, okay. So how will I write the rank function? So I'll take node f as x, or my target node, right? So now I want to find out the position of f when we do an in-order traversal of the entire tree. Will it be at the third position, the fifth position, or the second position, right? So for that, let us see what this code says. So here r is actually the rank of the node x, right? So first, in the first step, we actually find out r value, or the rank value. So it is equal to the size of left of f plus 1. So here it was x, but now our x is actually f, right? So size of left child of f plus 1. So what is the left child of f? It is d. So the size of d is 1, right? So size of d is 1, so 1 plus 1, right? And even otherwise, if you see that if I want to find out the rank of any node in a subtree rooted at that node itself, so I want to find out the rank of f in the subtree that is rooted at f itself. So the rank of f will be, or the position of f in the in-order traversal of this subtree rooted at f will be the size of its left subtree plus 1, right? So here we will get this value as 2. So now r is 2, and then my x is pointing at f, so I'll also make another pointer y point at the same position where x is pointing, right? So y is also pointing at the same position. So now there is a while loop which will run until we reach the root of the entire tree, right? So we are actually going upwards in order to find out the rank of node f in the entire tree, right? So what does this while loop says? The condition over here says that if y is equal to right of py, so when my y, this is my y, or the y is pointing at node f, so when this y is the right child of py, what is py? Py is the parent of y, right? So when I say py, that means parent of y, okay? So when my y is the right child of parent of y, then we perform this step. But here you can see that this is y and this is py. So my y is the left child of py, right? So we don't need to perform this step. We can just perform this step, which is out of the if condition, that is make y point at py. So we will make y point at py, right? So our y will point where py was pointing at, right? So now this will no more be our py because y is pointing over here. So its parent will be py, right? And then we will again check the while condition. So do this while y is not equal to root of t, but y over here is the root of the entire tree. So now this while loop breaks, and when we come out, we return r, right? We return r. So what was r? R was 2. So basically we returned the value 2, and that meant, so when we return 2, that will mean that the position of the node f in the in-order traversal of the entire tree is 2. And even if you cross check, you will see that when we do the in-order traversal, first d will come and then f will come. So the position of node f is 2, or the rank of node f is 2, right? So we took this example. Now let us look at another example. Now let us consider this node I as our x, right? Or we want to find out the position of this node I when we do an in-order traversal of the entire tree. So I can write the rank function as rank t, or the entire tree, comma I, right? So I want to find out the rank of this node. So again, I'll follow the first step in this function, that is r, or the rank of I, will be size of left of I plus 1. So what is the left child of I? It is g, and the size of g is 1, right? So this is 1 plus 1, so it is 2, right? So I found the r value. Now my y will also point at x, right? So y is also pointing at that node where x is pointing, okay? Then I'll go to the while condition and I'll iterate until we reach the root, okay? So if y is equal to right child of py, so if this is my y, this is my py, right? And as you can see, this y or I is the right child of its parent, right? F is the parent, so I is the right child of f, right? So in this case, we need to do this step. So this step says that r is equal to r plus size of left of py plus 1, okay? So I want you to tell me in the comments that why are we performing this step when y is the right child of its parent. Through a little bit of intuition, you can understand that why are we performing this step only when y is the right child of its parent. Why not when y is the left child of its parent? Please write it down in the comments. So here, the size of left of py, so this is my py and this is my left of py, right? So its size is 1, the size of d is 1, right? And my r was initially 2 plus 1. So the final value that I'll get is 4, right? So the value of r is 4, and now I bring my y to its parent, right? So y was initially pointing over here, now it will point to its parent, right? And py is not this node anymore because y has come over here, so this will be my py, right? So now let us check if y is equal to the root of t. Is f equal to the root of the entire tree? No, the node where y is pointing, it is not equal to the root of the entire tree. So we need to do one more iteration, and we will check if y is equal to right child of py. No, y is the left child of py. So we will not do this step, and we will just move y to its parent. So y will move from here to here, right? And this is no more parent of y because y has come over here. And then we will check the while condition. Yes, now y is the root of the entire tree. So this loop will break and we will come out and we will return the value of r. So now the value of r we got over here was 4. So we'll return 4. So this implies that the position of node I when we do an in-order traversal of the entire tree is 4, right? Even if you cross-check, you will see that in case of in-order traversal, first D will come, then F, right? And then we will get G, and then we are going to get I. So the position of I is actually 4, right? When we do an in-order traversal, or the rank of I is 4, right? So these were the two operations, that is the select operation and the rank operation, that now we are able to perform in our augmented red-black tree. And what is the time complexity of this rank operation? As you can see, we are moving upwards, right? We are following a path upwards. So the time complexity of this operation will be equal to the order of the height of the tree. And in case of a red-black tree, as it is a balanced binary search tree, its maximum height can be order of log n, right? So the time complexity of this operation is order of log n, because in each step or at each level, we are performing a constant time operation, right? These all are constant time operations, okay? So the time complexity of this operation will also be order of log n, right? First of all, we chose red-black tree as our data structure in the first step. In the second step, we saw that the additional information that is required in order to perform two new operations, that is the select operation and the rank operation, is this additional information. This is what we need to be stored in each and every node of our red-black tree. That was our second step. And in the third step, we saw that how will we perform these operations. So I wrote the pseudocode for the same, and I also explained it with the help of examples for both the operations. And in the fourth step, we have to verify that when we augment our data structure or when we modify our data structure red-black trees, so that in each and every node this additional information is stored, will that affect or will that reduce the time complexity of the already existing operations like the insert, search and delete. So as you know, the insert, search and delete operations can be performed in order of log n time, right? So suppose in case of delete operation, if I delete this node, right, or if I delete any node, in that case an imbalance will be created, right? And I have already explained in the red-black trees videos that when an imbalance is produced, in the case of deletion or insertion, we either do coloring or we perform rotations, right? So when we do coloring of different nodes of the parent of the deleted node or the grandparent of the deleted node, so in such a case, we don't have to change the size of any of the nodes, right? So when we delete a node, so as you can see, if we go along the path towards the root, the size of the subtree rooted at all these nodes on this path, upward path, will change, right? So initially the size of f was 5, but now it will become 4 because one of the nodes in its subtree has been deleted. The size of p was 8, but now it will change to 7. So what we need to do is that when we delete a node, we have to traverse along the path. So that will take order of log n time. But we found that the delete operation takes order of log n time complexity, right? So the time complexity of the delete operation is not increased when we add this additional information or when we want to update this information when we delete a particular node from a red-black tree. Even in case of insertion, if suppose we insert a node over here and an imbalance is produced, so we have to do two things, either coloring or doing rotations. So in such a case also, we might have to do some kind of updation in this size of x value for any node, either for the parent or the grandparent of the inserted node, right? We need to update this value for some of the nodes when we do insertion. So that is actually a constant time operation, whereas the time complexity for the insert operation is order of log n, right? So obviously you can find over here that there is no change or there is no increase in the time complexity of the insert operation as well when we add this additional information. So we have verified that even when we add this additional information and augment our red black tree to include two new operations, that is select and the rank operation, the already existing operations efficiency will not reduce. It will remain as order of log n, right? So this was all about augmenting data structures. We learned what do you mean by augmenting data structures, and then we saw the steps that we need to follow in order to augment a data structure. We looked at a very simple example of augmented stack, and then finally we learned augmenting red black trees through adding two new operations, that is the rank operation and the select operation, right? So that was all for this video. If you like this video, please share it as much as possible with all your friends and subscribe to my channel because I'm going to upload many such videos in the upcoming days.